In our previous lesson, Exploring Python Packages for Machine Learning Part 1, we explored the Python Pandas library and we learned how to handle tabular data sets using the Python Pandas library. We learned Pandas library is capable of doing many tasks you can do with any Excel spreadsheet package such as Microsoft Excel. You can use it for many data operations like you do in Excel. We first try to load a CSV file into Pandas library as a data frame and created the data frame object. And then we did some data manipulation tasks. We converted the data uh, columns from different data types into a data type we would like to convert into. And then we did some data manipulation work and we try to extract a new feature from a string column. And then we did some data exploration work. So we did descriptive statistics. We try to understand the data better. I told you one of the most important tasks when you get a data set or problems to work on, you should understand data better. So you need to spend a lot of time on data exploration, understanding what you are dealing with. So what data you are dealing with, right? So that consumes some time, like significant time in your project. So use that time wisely. So you will learn more techniques during this course, and you will get practice on how to use them. So in our previous lesson, we basically did some descriptive statistics, some data visualization methods such as generating histograms, box plots, and then scatter plots to understand the relationship between two variables. And later we get the correlation metrics from Pandas library. So all of these available within Pandas library. You don't need to load any other library. So the Python plotting functions, data visualization is available in Pandas library with the support of matplotlib library. And then you can use the correlation. You can create a correlation matrix also. Then you can get your dataset prepared for machine learning work with just using the pandas library. There are a lot of powerful techniques. You learn about querying to isolate your data. You learn how to generate frequency tables. There are many more to learn in the coming lesson, but the previous lesson was an introduction for you to start and to motivate you to work with pandas library. So in this lesson, we are going to work on scikit-learn library. The dataset you prepared using pandas library will be used to create a new model for this problem. So what is the problem we are trying to address in this project, or this you can think as a mini project. If you watch the previous video or you attended the previous lesson, you know we are trying to solve a problem for a used car seller to predict miles per gallon using the characteristics of the car, such as cylinders, number of cylinders in the engine, displacement and horsepower, origin, weight, model year, car name. So car name is not a feature actually. We learned last lesson. We're not going to use the car name, but the acceleration, the feature. So using these features, we are going to predict miles per gallon, and we learn how you can get the data preparation task done in a very brief way. Right? Okay, so now I'm not going to execute anything from the pandas work we did, the data manipulation task we did with pandas. So you can review that from the previous lesson. So I'm go down in this notebook to the section we start the scikit-learn. Okay, so in this lesson we are going to build and evaluate machine learning model first, and then we will try to apply that, and then we will try to examine what we can do with the machine learning model. Okay, so the first step of building machine learning model, assume now you have data prepared. So that data preparation again like will take a lot of time to understand and prepare the data for the project, and assume that part is already done. So we are starting from that point onward. So now our task is to understand few things. We need to first clearly understand what are the features we should be using to build this model. We may have hundreds of columns present in our data frame or our data set. We may have large number of rows present in our data set. So you, as a person who is building the machine learning model, you can be a data scientist or machine learning engineer or anyone who is building this model. You should do this in a very systematic way. You should not use everything available to you and put into a run using you can write a code to execute some task to get your model trained. But if you are not doing it properly, if you're not paying attention to what you're doing, you are just mechanically doing things, you will probably waste your time, waste computational time. If you're using, especially you are using a cloud computing platform, you're probably using time and money both. And also you will not be doing a good job in this model building process. You probably your model you are going to build is not going to be the best one you could build. Therefore, you have to follow certain steps. So here in this lesson, again, as an introductory lesson, I'm going to follow some basic steps to make you familiar with those. And in our future lessons, we will build a more understanding on each of these topics. In our very first lessons, we understood machine learning model as a function. The function accept feature vector, which is you can see in this equation as uppercase X, so which consists of a number of features. In your example, you can think of these are model year, horsepower, weight, acceleration. Those are your features. And then this function predicts a value. That value is we call a target or label in machine learning. That value in your case is miles per gallon. Your first task is to identify this relationship. What are your features to be used and what is your target variable? And then let's see how we can define it in Python, how you can tell the Python environment or in your code, what are the features to be used, what is your target variable. So the feature vector we can define as a list or an array. So here I'm going to define as a list of features. So the name of each feature will be name of column. If you remember what we did in our previous lesson, we can use the function in your data frame head to get a preview of your first 5 rows. And then you can find out what are the column names. If you wanted to get only the column names with another method, you can call data.columns. It will give a list of column names. Out of those column names, we assume like we decided to use one column, which is weight, to build a simple linear regression model. What we are trying to do is, using weight only, we are trying to build a model to predict value of miles per gallon. That is our target variable. Our feature vector will contain only one column, right? Your feature vector and your target variable should contain column names, presence in your data frame object, because you're going to use those variables later to tell the Python the scikit-learn library, the model we created to get the data retrieved from the data frame using the X label and Y label. We also create another variable called a Y predict label. So we created X label as a feature vector, and then Y label is the label or the column name of the target variable, and we create a new label. So this is not in your data frame yet, but later when we make a prediction, we build a model and we make a prediction, you should create a new column in your data frame. So that column should have a name, right? That name we are naming as Y label. We append that with the underscore predict. So that will make, let's see what we create here. So we are creating these 3 variables. One is X labels feature vector, Y label is just a string value, and another string value Y predict label, which is concatenating your Y label and the predict. Okay, so now let's try to execute this code cell, and then try to see what we get. So your feature vector is clear and the X label is MPG is clear, and the Y predict label, in future we will have a new column named MPG underscore predict. That's our predicted value column. Okay, so now hope you understood how we can provide, or we still did not provide anything, but we are trying to set up our Python environment. We are going to systematically building our model that we first identified X variables and Y variable, and then we created proper variables to use it in our model building steps. So now we have that X and Y variables figured out, and now we wanted to build a model object. Think this is the situation. You're hiring someone to do certain tasks, maybe at your work, maybe at your home. You wanted to hire a new person, a fresh person who don't know anything, but your intention is to train that person and then ask him or her to do their task. Right now, the person don't know anything about what he or she is supposed to do. Okay, this model creation we are doing next is very similar to that. To use a model or to train a model, like you're hiring a new you wanted a person to do certain tasks, you first need to hire that person. So in the model training, you first need to create the model object, a fresh model, then you can train later. So this is what we are trying to do now. From scikit-learn, so our goal is to build a linear regression model here, and then scikit-learn has different types of regression models, and the linear regression is in the linear model submodule. You can get the linear regression, you can create the linear regression model object by first importing the linear model from scikit-learn library, and then from the linear model you have the linear regression object constructor method, you can call it, and then you can create the model object. So we name it as model. So this will be a Python variable that called an object. What type of object it should hold? Linear regression object. So let's execute this first to import the scikit-learn libraries linear regression model, and then we create the model object, an empty model, so that does not have any training yet, just blank model. Later we will train. Okay, so now we have the model created. So now we can go to the model training step. So now we have X variables and Y variables. We have the empty model created, which is linear regression model. Now our task is to train the model. In scikit-learn, we have the function named fit. Scikit-learn has many different types of model, not limited to linear regression. There are other types of regressions, polynomial regression, and also there are classification algorithms you can use for machine learning, clustering, and many other types of machine learning algorithms available in scikit-learn library. But the scikit-learn library use an API. Pretty much all the machine learning algorithms to train a models, we use the function that is called fit. That's one way you can easily learn the library, because you are using the same function for function name almost all the time to get some task done with the model. You will see that when you are learning classification, clustering, and other models, right? So for the training, scikit-learn use the fit function, which is a function available with the model object. Okay, so you see the model object linear regression. If you print the model, you will see within empty parentheses, it shows you the model object is the type of the model object is linear regression. If you create a different model type model, you will see that model name and some other parameters when you print it. Anyway, so now let's try to explore how you can train the model. So you now know the model fit function is what you will be using. So what you need to provide into the model fit function. Okay, so as of the function definition we looked at earlier, so model you can consider as a function of feature vector, predict the value y. So what you need to provide to the model training, let's discuss it a little bit. This is a regression problem. Okay, what type of training method you will be using for a regression problem? We have mainly three types we discussed in our very first lessons: supervised, unsupervised, and reinforcement. Out of them, what type of training you will be doing here? You will be doing supervised machine learning with the regression problem. So you have to provide your features and your target variable as you have in the historic data. Think this is with this analogy. Think you are a teacher, you have select some students in your class. You're not going to teach any lesson, but your teaching method is to give them questions every day for 30 days. You give like 5 questions every day for 30 days, and you're giving those students both questions and answers. The task of the students is to learn how you can come up with the answer given by following the question. So the question to answer, the map should be generated within students' mind. So they have to study. They can do studies, and then they can find out what is the map between question to answer. I think these are like some arithmetic problems, right? So that might make it much simpler to understand. So then students do this exercise for 30 days. Every day, get 5 questions with answers. They solve it, not solve, but they try to solve and compare the answer. And then if the answer is not correct with the teacher provided answer, they try to find out what is the issue and try again. They try until the correct answer is achieved every day. So they do this for 30 days. After those 30 days, teacher is going to provide a test to know how well these students learn. Okay, so keep this scenario for now. I'm going to stop that scenario at that point, but now let's focus on the first part. Teacher is going to provide both questions and answers at the same time. The students are trying to find the relationship between question and answers. This is simply what we are doing in this supervised machine learning. So the questions here, they're not actually questions, but your features. So your model is trying to find out the relationship between your features and the target variable. So that's the model. That relationship is what you are going to build as the model later. How you can come to this target variable from the features. So what the model actually does is it will try to come up with some relationship and predict a value and compare with the target variable, the actual target variable. And then if it is very different, it's trying to adjust that method of coming to the answer, then to the prediction, and then that process happen iteratively. You can think of in very high level that is going to happen, and then later come up with the optimum model. Okay, we will learn this in detail in a future lesson, but for now let's think that way how the model works. So to do that task, you need to provide your features as well as your actual y values. At least you know right now from your data, because you have a column of miles per gallon someone measured for you, right? Someone already collected that data, so you're using that to train the model. The model will train based on your features and your target variable. Okay, I think everybody is clear with that. So then we can execute this line, then we can train the model. So since we have a relatively small amount of rows available, so we have 392 rows and we use like only one column, this model training is much faster. In some machine learning problems, if you are using large number of records or large number of, we can call them as observations to train your model, and if you have large number of columns present as features, your model training process will be time consuming. Probably it will take minutes, it could be taking hours. Some machine learning problems, it will take days to come up with a solution. That's why very important to follow some systematic procedure and follow correct steps in data preparation, setting up your model, choosing correct set of variables, because sometimes you cannot repeat things multiple times. Again, like time consuming, resource consuming, and you have to build the best model out of it. So that makes you make you a challenge, right? So you have to accept that challenge and act accordingly. Okay, so now we have a model train. Now remind what I told in the beginning of the lesson. The scenario: you are hiring a person to do some task, but the person don't know how to do that task. A fresh person, you are training. So now this model you hired, you train, it's well qualified to predict. Now predict means you are going to predict a value from a given set of features. Those features you can get from a new car, which you don't know the miles per gallon or the car efficiency. So new car comes to the seller, and then he can provide the information such as horsepower, model year, weight. But in this case, your model is built only on weight. If someone provide you the weight, you should be able to, or your model should be able to predict miles per gallon. We don't know how much accurate that prediction is. We don't know how good the prediction is, but it can predict. It qualified to predict, right? You trained the model. So let's see how we can get more information about the model train. If we wanted to get the model parameters after it trained, in a linear regression, we learn in our lesson, in the very first lesson, the linear regression you can write like y equals a0, which is your intercept. A1 is the coefficient of, so A1 times coefficient of 1, the first variable, and then A2 is the coefficient of second variable, which is x2, right? You can keep going up until the number of variables you have. The most simplest equation, linear regression equation, we are familiar in our education also, y equals mx plus c. I think everybody familiar with this. So this is a linear regression equation with one variable, and we call it a slope and intercept, right? So here, this is, you can think of this is a1, this is your a0. All right, so now our very simple model we built like this one. So what is our x here? X is our weight, and a0 will be our intercept. That is what we should be finding in the model training. Okay, so I talked ahead. So in the model training, what actually happening in a general linear regression model? The model is trained to find out what are the optimum values to this A0, A1, A2, A3, etc. Okay, in our simple model, the model training happen, and then what actually provide you the value of A0 and A1. Using this A0 and A1 value, you can reconstruct this equation, and then you can use it anywhere you want. You can create an Excel spreadsheet when you have a column of weights of cars, and you can predict by applying this equation. This is a simple equation you can create in Excel. Okay, so now let's find out what are those parameters. So what are the coefficients? Where a1, a2, a3, and what is the intercept, which is a0. So let's see what your model is providing you. So we now know the coefficients we can get from model object, the trained model object. You can call the attributes coef underscore will give you the coefficient list of coefficients variable you have in the model. So right now we have only one variable, and then to get the intercept, it's only one value per model. So model dot intercept, it's also an attribute, intercept underscore will give you the intercept value. Coefficients, remember coefficients will return a list or an array of values. Intercept will return only a single numeric value, right? To make it a better representation when we are printing it or when we are storing the value, I would like to store it in a data frame object. Because coefficients, even you have one coefficient, later we will add more variables, we will have number of coefficients, then we have the intercept. So we can make it a data frame out of it. So here I'm going to create a data frame for coefficient the coefficient listed with the variable name together, because otherwise this will only return a list of numbers or an array of numbers, but it does not contain which variable this coefficient belong to which variable. We have to construct something to make it like nicely displayed or store it for future use. So I'm going to construct a data frame object. You will learn about this in a later time, but for now, just get the idea. So this is the constructor method for a data frame. What we did in our previous lesson was to load a CSV file into a data frame by using read CSV. That is one way of creating a data frame object in Python by loading a file, loading a data file. You can also create a data frame without a data file. You can convert other variable, you can combine other variable types such as list, arrays, or dictionaries. You can convert into a data frame. So how you can construct a data frame is using this data frame constructor method, pd.dataframe. To construct a data frame, you have to provide some values. This is one way of providing data into a data frame constructor. You can provide data as a dictionary. So this dictionary will contain two key values. So first value is features, second value is coefficients. So now you have some if you have a good understanding from our previous lesson, this feature should become a column, coefficient should become another column. So this should be two columns. So what each column should contain a list of values or an array of values per column. So this X labels is a list of values which you already have defined above, which is your X labels column or which feature vector, or the list of column names to be in the features. And then coefficients is something you got from this step by calling the model.coef attribute. Okay, so these two values will be two list or array items. So you can convert into a data frame by providing within a dictionary as a key value pair, and then you will construct a data frame object. So this is what you get, a data frame object. Since you only have one value as a feature, so you have only one row. For the intercept, I'm just simply printing the intercept value. So to make an output, you will see it here. All right. So now let's try to predict the value out of from the model. So we are going to assume like we have a sample value. Someone just say, okay, can I predict miles per gallon? My car weight is 2,500. I believe this value is in kilograms. That's also important to know. Remember, like when we are discussing about the data, you should know what is the unit, etc. But assume like this is 2,500 kilograms. That's the weight of that person's car. So now you know to predict miles per gallon of that car by using the model we trained. So now your model is well qualified to do that task. Okay. Then the model prediction will happen like this. You're calling a function. This is a function now available in the model object. You're trying to provide a list of features, right? So the predict function will accept list of observations. Each observation should have a feature vector. So in this case, you have only one feature, and also you are providing one observation to predict value. So you're providing the test weight. You can just provide the value 2,500, but since we already created the variable, I put this test weight. This is the variable value, the number. Put within the bracket will make a list. Even though you have like a one item in that list, so that's still a list. You're providing that as your feature vector. You're providing list of feature vectors to the predict function. It will predict the value as 27 miles per gallon, 27.09. It will return. So what it is going to return, the model predict function will return an array of your miles per gallon values. If you provide two features, let's do that. Why don't we do that? So let's create a new column, a new code block or code cell, and let's provide two values. So one car, assume you have 1,500, a lighter car, and another car, I will say to 3,500 kilograms. the heavyweight car. So you provide two. Is this correct? No. What you should provide to the model predict list of feature vectors. Okay, so the first feature vector, you have to close it for the first car, one feature. The second feature vector, you have to close it for the you should make it a proper list or a numpy array you can provide. So this will make a one first feature vector, this will make a second first feature vector, and this is the second feature vector for car 1, car 2. So let's see what we get here. We get two values. So this will give you the miles per gallon as the 34.74, for weight is 1500 kilograms, and miles, so miles per gallon is 19.4. The second car you will get 19.45 for the weight 3500. So now you see, when you provide a list of feature vectors, you will get list of values as the output, or the y value, or predicted y value, not the original value, because we don't know for this 2500, 1500, or 3500. They are new values. We don't know the miles per gallon as you use the data set for training, that has the weight and the value. But these values we don't know, they are the new values. No one measured, as you assume, no one measured the miles per gallon, but you're going to predict using your model. Okay, so now we know how to use the model.predict function to make a prediction from your model, using your model, giving a new data, a new feature vectors. Okay, so now let's try to predict the miles per gallon for the same data set you used for the model training, but because we wanted to compare how good our model works. Okay, so we are going to use the features, list of features from the values from the observations we had in our training data set. We provide into the predict function. This is how you can provide your feature vectors in terms as a data frame object. You can isolate only the columns. We learned about how to isolate columns when we are doing the correlation in our previous lesson. When we are generating the correlation metrics, we learned how to isolate a set of columns from the data frame. You only get the columns of belongs within like the X labels or your features. In this case, only one column, but still you can provide that as X labels. And then you pass it to the predict function. Then you will generate a new column in your data frame that will get the name we label above. So we assign this y predict label as mpg underscore predicted. Right? So if you wanted to remember that, so you can go above in this notebook, you will see the y predict label is mpg predict. So you should create a new column right now in this after executing this code block. So that should contain the predicted value for the all observation in your training data set. Okay, so this step does that. So let me demonstrate that in a different code cell, so that will make it easier for you to understand. So let me use the head function from this new column you created to see what you have. So these are the predicted values for each observation, the first 5 observations in your original data set you use for training. Right, so you now have for each row you should have now the predicted value as well as the actual value. So what you can do with those two, you know the correct answer, you know the answer you got from the model, you all obviously you can compare them, and find out how good your model predicted these. So what is the simple comparison you can do? We can find out the difference. What is the difference between the actual value you available only for this data set and also the predicted value, right? In that comparison, you can do that comparison simply by subtracting pandas column from another column. You're subtracting the value of actual value, which is the miles per gallon already available in the data set, and you're subtracting the predicted value from that value. So this is a column operation in pandas data frame. Could be something new to you. I did not discuss earlier in the lesson we did with the pandas data frames. but this is now you can learn that as well. So this is a column operation you can do. You can subtract one column by another, you can add two columns, you can multiply two columns together, you can divide one column by another, you can do column operations like this. You can take a series out or a column out from your data frame and you can operate. You can multiply by a scalar, or you can operate with a scalar, or you can operate with another column. So this is a simple subtraction. So this will create a new column. That column you need to assign to a new variable. Now you can connect this. If you are familiar with Excel, I know most of you can connect this with your Excel formula you create, right? You are doing some column operations by writing a simple formula. So some complex formulas also you can write in Excel. Then you are creating a new column with the result. So this is very similar to that. Okay, so creating a new column named difference. Let's see how the difference column looks like. So we see in this preview, even if you don't use tail or head, this Jupyter notebook will only print you first 5 rows and last 5 rows by default, unless you change some parameters. We're not going to discuss that now. And then what you see, the first row, you get a difference is negative 0.142. And then these are like, we can see like pretty much close, but this one, the miles per gallon is 44, actual one was in the data set originally. And the predicted value was roughly 30. We have like 14, difference of 14. We are predicting value much less than the actual value. So 14 less than actual value. Okay, so that's not very good. So your model did not work very well, at least for this car. We don't know the reason, but if you do some advanced study, we can find out what is the actual reason this happened. There could be other parameters we did not use in this model. We use only weight to predict, right? If we use other parameters, we can mitigate this issue. Okay, so other stuff like the last one is 31 is the actual value. We predicted 5.5 less than the actual value, or 5.6 less than the actual value. These things happen if you don't have sufficient variables, if you're not using proper variable list to predict, and if you don't have the variable transformed into a very good form to make the prediction. There are many reasons your prediction is not going to be good. But in our machine learning model building process, our goal is to make this prediction uh, closer as much as possible to the actual value, right? We may not create a perfect model, but we should make it closer as much as possible. Our model prediction should be accurate as much as possible. It should be precise as much as possible. Okay, so we will learn how to achieve that in our future lesson when we do model evaluation. But in this notebook, we are briefly going to discuss about model evaluation techniques for regression models and how we can use that to identify our model is doing better or not. This is a very high level and very brief introduction, but you will learn a lot. So keep paying attention. Okay, so now you know the getting the difference, but difference will not give you like a good understanding, because you cannot go through. If you have like millions of rows, you cannot examine row one by one, right? You have to have some other metric. In scikit-learn, we have different metrics we can use to evaluate the machine learning models for classification problem models, regression models. We have different metrics to the evaluation. So we will discuss two of them down in the notebook relevant to regression models. But before that, let's try to identify, or let's try to visualize our results using matplotlib. So here I'm trying to plot the predicted value versus actual value, right? Or the predicted value against actual value, you can say. So your x-axis will be your actual value, miles per gallon, recorded in the data set. And the predicted value is the value predicted by the model, but only by using the weight. The red line will represent in a perfect prediction. You should get your predicted value and actual value should be equal. So that's the red line. You see the values you predicted with weight is not following the straight line. It's going to be a straight line, but it's going above the expected straight red line here, with slope 1 in this case. And it's going to be plateaued at some point, and it's not going to increase or anything. But the beginning and end are close to the actual, but there are some points here and there in the middle as well. But in majority of the points are following a curve path above the expected line, right? So what you can see here is your actual values are predicted as higher than the actual value always. So you are kind of over predicting the value in this exam. Okay, you follow the curve and then plateau here, and then it's not following the line exactly, but most of the things above the line, most of your predictions are above the line. Okay, so we think we can assume the model is not working well, but it's doing something, predicting something, but it's not a very good model to be used. Okay, so we have to think like how we can improve the model in this case. So let's try to quantify this in a later cell. In the code cell, we are going to use scikit-learn for proper metrics to quantify this and try to understand it better. Before that, I wanted to pay attention to this matplotlib, how we can plot. We learned about this matplotlib functions before, how we can use matplotlib to generate a plot. But I wanted to review this again to help you to improve your understanding, and also to compare what we have in pandas library can simplify this the maybe 5 6 10 code to 1 or 2 lines of code, right? So here is how we can use the matplotlib to plot something by using the matplotlib functions. You can use the plts.scatter, data y, data x, those things, right? But if you want to do the same thing in pandas, so what you would be doing is, I wanted to show you here as well. So you will be using plot. So you will be using the kind. You can now remember what we learned in the previous lesson when we are doing this. What kind of plot you wanted to generate here? Scatter. And then we have to provide what is our x value. What is our x value here? Is your y label, which is your actual value. We don't need to put quotes. We have the variable created as a string value for that column name, and then your y value, y predicted label. Okay, so we can create the same plot just by one line. What you don't have is this red line that can also be included with another line. We can plot another line, maybe like another line or two. You can include this red plot as well, but you will get everything done. You don't need to do all these things if you just use pandas library. So that's why the pandas library is very powerful tool. You should be familiar very well, and make sure you understand the functions and how you can use these functions to your work. Using the like learning the function, doing this code mechanically is not going to help your data science or machine learning career. What you can what it help you to understand how you can use pandas to do certain tasks done, right? So sometimes you don't need to you need to follow some out of the box ways of getting tasks done in most of the data science and machine learning work. So therefore you just need to get familiar with what is available, and make sure you combine multiple things and make the proper use out of it, not just using the boilerplate code, or you not just following some template all the time. So you have to think and act accordingly. Use pandas as a tool. The tool should be able to shape the things as you want. Be creative in that case. Just a side note. Okay. All right. So now let's try. We learn how to visually look at one way. So there are many other ways you can visually look at the regression output, but you can think of this as is one way of looking at. So then let's look at from a metric. So get a proper quantification. We get a number, not just a visual representation, but a number you can compare later. Right? So if you have two diagrams visually, even visual diagrams, diagrams or plots, we can easily understand or get the story out of it. But comparing two diagrams is not easy. Comparing two numbers is much easy, right? So therefore, we will get mean square error. The mean square error is nothing but to get the difference between your actual value and predicted value, as we already calculated above, and get the square value of it. So you square it and raise to the power of 2, in other words. The reason why we are doing that, the reason is, if you notice above, we should get when you say y actual minus y predicted, you could get both positive and negative values as the difference. To compare negative and positive is not that convenient when you are combining them into a one value. So it would be better if you make it all positive. One way to do that is to get the square value, or you can get the absolute value. There's another metric you can use, mean absolute error. Instead of doing the square value, you can get the absolute for, within this parenthesis, absolute value of the difference. That's called mean absolute error. We will be discussing all of these in a later lesson, but here I'm using the mean square error. And then divide, why it comes to mean is divide by total number of observations in your test sample. The difference squared, sum them up, divide by total number of observations will give you the mean square error. Okay, that's one metric you can use to find out how good your model works. So then let's try to find out another metric, which is R square. We call it like coefficient of determination, or R square. So this one I know you used in your other lessons as well. If you studied physics, or if you did science experiments, you always find out R square value of linear equation. You get like y equal mx plus c, and to justify how good your experimental findings with the equation, you always present with the R square value, right? We all know what is the good R square value and not good R square value. So R square, when R square value is close to 1, we always consider that as a good fit. When R square value is close to 0, or it's going to like 0 0.5, 0 0.6, so we going towards 0 from 1, so we think like the model or fit is not that good. Okay, so this is how we can calculate R square value. And I'm not going to go into like detail of these equations here, because we are going to discuss this model evaluation in detail in our lesson of machine learning model evaluation. So therefore this I just put into your understanding. Okay, so even though we need to understand how we calculate them and what they represent, what is good R square, what is bad R square, you don't need to do any coding in scikit-learn. Means like you don't need to type codes to calculate these values, right? So scikit-learn provide some easy ways or functions to get this calculation done. So under scikit-learn metrics, right, you can import two of these functions. Mean square error is the first function where you would use to calculate mean square error, and R2 score is the function you will calculate R square. Okay, I'm also using the NumPy library here because I wanted to get a square root value. NumPy has a square root function, that's why I'm importing the NumPy as well. Okay, so now you know, use the mean square error and coefficient of determination from scikit-learn. You need to import these two functions from scikit-learn metrics. Okay, so I'm going to use them here. MSC, I'm creating a new variable. We should return the function should return a value. The MSC is a numeric value. I'm create variable containing numeric value. I'm going to create that value by executing the mean square error function from scikit-learn metrics and providing a list of my actual y values and list of my predicted y values. So we provide list of predicted values and actual values, and then it will calculate the mean square error. I told the word list here. You can provide a pandas data frame column or a series in terms of list, or you can also provide numpy array, right? Your y values and the predicted values you can provide as numpy arrays or pandas data frames, data frame columns, or you can provide as two lists. So what happened if you compute this, it will create a value. So MSE will return a value. So that value you can print here. Okay, so this is mean square error. So what is the problem with mean square error is we always have the value, the error value is if your miles per gallon, right? So it should represent a unit, miles per gallon, right? That's the unit. So the value error or error value if you take the mean square error, so that mean square error value is in miles per gallon. That unit should be squared, so it's not in the same unit as your predicted values. If you wanted to take into the same unit, you need to get the square root of it. So that's why you can use the root mean square error. The mean square error is squared. You can take the root mean square error. When you report a root mean square error, your error value is in the same unit as uh, your predicted value. So your error value is also in miles per gallon, right? R2 score does not have any unit. A value between 0 and 1. 1 is the best case, 0 is the worst case. Okay, so these are like three metrics. So to get the square root of mean square error, I'm using numpy sqrt. So sqrt is a numpy function. This could be new to you if you are not familiar with numpy other than what we learned in the previous lessons. So np.sqrt will give you square root of a given number. So let's try to execute this code block and find out what are those values. Okay, so the mean square error is 18.6 and root mean square is 4.3 and the R square is 0.69 roughly, approximately. Okay, what you can tell with this mean square error? Can you tell anything about how good or bad your model? Not that much, right? So we just build one model. So we get mean square error is 18.6 and the root mean square error is 4.3. We can say the value is 4.3. The value we predict is should be within 4.3 plus or minus. We can just roughly say that, but that's not going to tell you a very good idea about how good your model is. But R2 value or R2 score or the R square value should give you some hint of how good your model is. What you can tell with this 6.69 value. The model is probably not that good, but it's doing something, but it's not good enough. So we should think of like improving it, right? So we can, if we can make it to close to 0.8, 0.9, that would be great. So let's try to find out whether we can do that. So now our goal, we have now these three metrics. We can use two, maybe either mean square and R2 square to compare with the next model. So now we are our goal in any machine learning project. So if we build one model, we are not going to satisfy with it. We wanted to build number of models. Okay? We probably need to build models with different combinations of features to find out which set of features is going to be make the best model. We probably build models with different algorithms. For regression problems, we can use different regression algorithms. For a classification problem, we can use different algorithms, right? So in the regression, we can have this linear regression, we can have tree-based regression model, tree-based regressors, and we can have neural networks to make the regression models, right? And for classification, we have different types of algorithms we can use. So we will try out different algorithms and find out which algorithms is going to be the best predictor. Okay, so in this attempt, in this very introductory lesson, I'm going to do with this notebook, I'm going to take an approach of starting with one variable. That's what we did above. Start with one variable and keep adding more variables and see whether we can improve the model. Okay, this is what we are trying to do now. So as the next step of improving the model, so what our strategy is to add more features. I'm going to add the horsepower. So let's add it. So now our feature vector here, we have two variables, weight, we had already in the previous model, and then the new variable horsepower. We fit the model. So this is the same thing we did above. The same steps we following. We define our feature vector. Our y label is not going to change. It's still the miles per gallon. We train the model with calling the fit function, providing the new set of features. You are retrieving these two columns from the data frame, right? And then you are taking the y column from the data frame as a series. Remember, for the x, you have to pass two-dimensional array or a data frame. As the y value for the fit function, you have to pass an array or a series from a data frame. Okay, so two-dimensional array, one-dimensional array, data frame, which is two dimension, uh, and a series, which is one dimension, a column. Okay, column is your target column. So when you pass this into the fit function, it will train your model. Now your model is retrained with two variables. Should be much better. Let's assume that, and we can verify. And then we can get the coefficient, list of coefficients and intercept value. And then same as we did above, I give you the detailed description. If you want, you can go back and review what I described about the creating data frame object from the coefficients. Let's execute these steps. Oh, sorry, let me go back. So what we missed here, so we have a typo here. We, instead of x labels, we have x. So let's execute again. So we now have two variables. We fit the model, we get the coefficients. This is the list of coefficients. For weight, we get this value as the coefficient. Horsepower, we get this value as the, and this is the intercept. Don't try to compare these weights with the previous model, because that has nothing to do with the value, because when you add more variables, you will see different values comes every time. So it's not just good to compare them, but the comparison you should be doing is with the model performance, which is mean square error or root mean square error and R2 score. Okay, so now we trained the model, we got the coefficients, we know now how to by now you should know how to reconstruct the linear regression equation by using these coefficients and the intercept value. If you would, you can do that. And then let's try to make the prediction routine, run the prediction routine. So make the prediction for your training variables, so, using the x variable x features in your training data set, and try to find the difference, right? And we will learn the difference does not be is not to be the best way to get the idea of how good your model is. We have to get the other metrics, but you can always plot and visualize your prediction and the actual value to see whether they are coming along, and whether it's they are over predicting or under predicting. So I will show you that in the next one. So let's try to execute. Okay, so now see, we have we did visualizing the actual value and the predicted value. So predicted value against the actual value, and the red line, as we explained above, this should be expected, but we still have the over prediction scenario. So you are predicting the value higher than the value it should be from the model. Okay, but if you compare the two diagrams, we now see the points are coming along to a line, or the like a towards the line, but still it's not going to be a good one. So let's try to find out what are the model evaluation metrics we have. We get the mean square error is 17, root mean square error is 4.2, and the R2 score is 0.70. A slight improvement compared to what we had above, 18, 4.18.6, 4.3, 0.69. It's a slight improvement after adding weight, adding the horsepower to the variable list. So 17.8, 4.2, 0.70. It's a slight improvement to R2 score. But now you can compare mean square error between these two models. Now you can think, okay, this model is better than the previous one. Of course, yes, by using both the mean square error and R2 score. Okay, so are we going to satisfy at this point and say, okay, this is the best model we want to build? No, we have to keep doing it until we guarantee that we cannot do more, right? So we have to give our best model to the client, or best model we should create to the use. So now let's add another variable. So let's add the model year as the variable. But before doing that, I wanted to think another way, or apply another learning you get from the previous lesson. We learned how to create functions in Python. So now we are going to, in machine learning or data science, if you want to do repetitive tasks, right? Is it good to write code every time when you want to do the same task by changing some variable value, but we are executing the same thing? Should we copy the code from one block to another block? No, right? If you are familiar with software development, you probably will not do that. You create a function to do that task. So what is the repetitive task we are doing here? The repetitive task here is model training. So why I'm calling it a repetitive task? You are following the same set of instructions or same set of steps, right? You're writing basically the same Python set of Python lines or codes, but you're only changing actually one parameter in the last two attempts of training the model. We only change the variable x labels. Earlier we had a feature vector with one column. Next time we had a variable with two columns. Why can't we convert this training into a function? Model training steps into a function, right? So everything we did above, we can put into a function. So that function should accept your data frame, feature vector, target variable, and the model you should be training. This function is useful to train not only for this problem. You probably can use it for a different problem as well. So you are making your this repetitive task into some useful function. You can not only use in this problem, but of course you need to customize these plot labels later, but you can think of that also included in the function as a parameter. But you can make it a useful function. The function I name is predict milespec and accept data frame, feature vector, label, y label, or y column label, and the model object. The model object you would train, right? The other things will be automated. So this is another thing we need to pay attention in our machine learning workflow. If you can automate something, try to automate it. If you can convert into like a function, in a repetitive task into a function, convert into a function and use it. Don't just create a code like a lengthy code unnecessarily, right? And and also you can reuse some of the things in different projects as well. So what are the steps we are following again to remind you all? We are creating we are just verifying the labels via X label, Y label. We need to have a checkpoint, otherwise we want to know what we send to the function is working properly. So that's why I created a checkpoint to make sure we are tracking the correct set of X labels, Y label, and Y predicted label. And then we do the model prediction. I don't need to describe this again. We are calling the fit function in the model object, providing X feature vectors, list of feature vectors from the training data, and then target values, and then getting the coefficients, list of coefficients, and the intercept value, creating a data frame and displaying the model function, which is the coefficients for each variable and the intercept value. And then we are predicting. So this is like the prediction. I will predict. I'm making the prediction for the data set again, and we will have a predicted value for each and every value in the data set, and then we can get the difference And then here, like if you wish, be sure you can print the difference. So you can say print the difference value. Uh, and then what we are trying to do is, after predicting, and then we are trying to plot plot it as a scatter plot, right? So we create a scatter plot of your predicted values versus the actual value column, and then also we draw the red line, which should be the expected ones, and we put the other labels, etc. And then what we are going to do is we are going to get the model evaluation using the scikit-learn model evaluation metrics, mean square error, root mean square error, and the R2 score. So this workflow, you can put all things into one function and execute once by providing those parameters above, like we mentioned: data frame, xlab, feature vector, target variable name, and then the model object. So let's try to execute this. This create function, it will not return anything, just creating a function. Now we are trying to use the function. Okay, so it's a typo here. So apply model training function, and x labels we define here. We add model year. So now we have a feature vector, weight, horsepower, and model year. So this we're going to provide in this place. Data, nothing is going to be changed, so we have the data set already loaded above. And y label, nothing is going to change. If you wish, you can have the y label as mpg. The model object we created above, we don't need to recreate. If you wish, you can recreate here as well, but you don't need, because we already have it created above. So now we can execute our training function and get the model trained with 3 variables now. So now we do everything at once. So see, like this, when I execute this line, this function will execute everything as it defined in the function, all the steps, and also print the output as we instructed within the function. So we first say, like, okay, give us the variable list, and what's the target variable name, etc. And then after training, we get the feature coefficients, and then the intercept values, and then we get the difference between predicted and actual. Remember, like the earlier we had like 44 versus like the 14 difference. We get closer into 10, so we still not get the best one, at least for this car, but other cars is getting like a close value, right? This is very good prediction, and this is very good at very close, like that. So in the visual output, we see it's trying to get closer to the line, the red line, but still it's over predicting and having some curve, and the plateau is getting like diminished a little bit, but still not the perfect. But you will see from the metric, it's going to be a good improvement in terms of r square value. From 0.7 to 0.10, it's a big improvement actually. The mean square error also decreased into 11 from 17. That's also a good improvement. And root mean square error is also got improved, 3.4 from 4.1 above. So we are doing good. Like we are adding like a new variable model here made a significant difference to the model training process. So model is now trained better than you trained with only one variable, which was weight. All right. So yeah, going into the correct direction. So now we can keep doing this. We can add another feature. You can drop one feature. So actually that's something you can do. You can not only add new features from your feature list available, you can drop another feature and see whether it's going to improve this R2 score or mean square error. You can track one metric, or you can track multiple at a time, and see whether you are going to do any improvement to the model by changing the feature list. So this is our strategy in this notebook, at least, to play with the feature list and make the better model. So there are other strategies you can use. Like I mentioned, you can train with different algorithms. Within algorithm, you can change the algorithm behavior by changing some parameters we call hyperparameters. Again, that we will learn when we are learning how to tune your machine learning model with model evaluation later. We will learn in this class. And then you can do that. So but here, like, our strategy is to play with the list of features. Okay, that's the introductory lesson. So you can do these intermediate steps, adding and removing features, but as the last step in this notebook, what I'm doing is I'm throwing all possible numeric columns into the model. So I'm creating a new feature list. Okay, the feature vector I can call, and I will also copy this y label to make it clear to all of you. So my feature vector will be all possible variables: weight, horsepower, model year, cylinders, displacement, and acceleration. My y label, or the target variable, is what we are predicting, miles per gallon. So now I'm using the same function created above, the predict mpg, passing the data frame, passing the new feature vector, y variable, model object, because we wanted to retrain the model with new feature vector. See, like, how useful the function we created above. This is what you should be doing in terms of doing your work better. So you have to think again, like, if you can automate, if you can create functions for repetitive tasks and then automate, so that would be better. So try to do that and to make a better best use of your time, and as well as it will save your time, computational time, and some money if you are using cloud platform. And also you can if you wanted to transfer this function into a different project, you can also do that without spending another time on building the model training steps to a different project. Okay, so this is a side note. Let's execute this the model training routine for the new feature set. This is very fast because I mentioned it's small data set, a small model. So we trained the model. We now have like a feature coefficient list of feature coefficients for 6 features. See the different features for each coefficient, and then the intercept value, and these are the difference between prediction. You see some improvement here, the one we had, like, the largest error or the difference. And then the visual output. So we still see the over prediction situation, but the curvature is also here, but I think it's getting along. Okay, at the end we got not much difference from the last attempt, but we got like slight improvement, 0.809 as the R2 score and 3.40 as the root mean square error. Okay, we're going to stop iterating through the model building steps. So it's your task. You can try it out with the different combinations of variables and think what you can do better. Make this number. So what our goal in this machine learning model building is to improve the model by these numbers. So you can get the R2 score into maybe 0.9. That would be great. You can minimize this root mean square into a like a lower value, much lower value than this. That would be great. Having that goal, you can do a lot of things. You can experiment with things. You can try out different things. We will learn how we can do systematically, and how we can do other data manipulation techniques such as transforming these variables and try out the transformed variables to make the model better. Okay, so that the last point, so I wanted to show you the regression equation. Okay, so let me go here. So the regression equation, uh, we can show it like this. So miles per gallon is intercept plus coefficient 1, you will find above, times weight, coefficient 2 times horsepower, coefficient 3 times model year, plus coefficient 4 times cylinders, plus coefficient 5 times displacement, plus coefficient 6 times acceleration. So this will be your linear regression equation, where you can use in Excel spreadsheet, or you can put into another program code. The linear regression problem you can easily transfer into another platform. You don't need to use Python to do the computation in the application actual one. But some other Python models, you cannot do that, such as tree based models and some complex models. You have to use Python even to the prediction. But linear regression models, you can train the model, get the equation, you can transfer to another platform if you need. Okay, so this is the value. If you put the actual coefficient values in place, your equation will be like this. Okay, so now I hope you got some understanding of the basic machine learning workflow using scikit-learn library, how to train a linear regression model. We will discuss in detail how we can train the linear regression model, but I hope you will get a basic understanding, and that understanding will be helpful for your future lesson. Therefore, please practice again, like I'm telling multiple times, please practice with this notebook, and then you can capture the future lessons very well if you do that. Okay, so now we come to the end of this notebook. I have like few more questions for you. You would provide me the answer, but or you can think of the answers by yourself. So what standard practice we missed in this model training process? The hint I'm going to give is this is regarding the data used in for the training. So what standard practice you would be using? If you're learning machine learning, you never had any machine learning exposure before taking this course, you don't know this, but I will briefly, I mentioned this briefly one time. That was the model training, the data set you use for the model training. That's one of the basic thing we missed here. Should not be used to evaluate or test your model. Okay, so I gave you the example of a teacher and students. Students get 5 questions per day for 30 days, and they train on it, and they learn how to answer those questions, and then teacher is giving an exam. Okay, so now that's the part I stopped at. So when the teacher is going to give an exam after 30 days of studying questions and answers, no other teaching, like students only work on questions and answers. For the teacher to test whether students understood or student learn well or not, what should the teacher do? Should the teacher give questions from the test questions from the questions students used for the study? No, right? So if teacher gave the questions where students have answers during that 30-day period, probably some students can memorize questions and answers. Sometimes our students do that, right? Students memorize and get better score than the people who really understood the subject. So this can happen, right? A student, sometimes student one student can don't may not understand anything about the subject but memorize things, and then go to exam and write the paper and get a very high score. But the student who understood the subject well probably will get an average score. That can happen in actual test as well, but the machine learning, we have to pay attention to that scenario, so we should avoid that. If we use set of features set of features, or like we use our part of our data set for training, we should not use the same part of our data set for the testing or evaluation. Same as the teacher should not use any question from the questions students already have answers to test the knowledge, student knowledge in the final test, right? So therefore we are doing a technique called train test split. This we will learn in one of our coming lesson. So we are assume like this, we have 392 rows. We're going to take maybe 300 rows. We isolate them and take them as our training data set. Okay, so the model is going to train with those 300, and the rest of the 92 are not part of the training. We only use them for the testing or evaluation. That's what we are using to calculate the R2 score, mean square error, to get the evaluation matrix. So there are problems. Probably you have that question in your mind. So this is like a small sample. So now if we connect this to our sampling lesson, we probably miss out some of the groups in this sample, some since we some of the groups uh, or some patterns we are going to miss out in the training, and we are not going to capture everything we should capture. So we are using the full data set to the training, right? So there are some issues. We are going to discuss them in detail when we are doing the model training and model evaluation in a later time. So, but we have to practice that train test split. Sometimes in a simple problems like linear regression, this is not going to be a big effect. But if you are doing other machine learning models, so you should strictly follow that train test split. If you have small number of data sets, data like this, 392 is small compared to a regular machine learning problem. You would expect to solve like this. You probably would consider some techniques like so you would consider techniques like cross validation, called like k-fold cross validation. So that could be another method. You will be using all the samples, but the technique I'm going to describe in a future lesson. But you will still do the train test split internally. Okay. Okay. So this is the question one. The second question is what you could do better in terms of the ranges of input features. So this is an interesting question. You probably will again will come back to this one in a future lesson. So what you see here in when we get the data description or the descriptive statistic, we get the mean, minimum, and maximum values, right? And also we get the mean value. So I already mentioned to you when we are doing the pandas part in this lesson, the previous part, weight is in few thousands, and the number of cylinders is like less than 10. So these are in two different scales. In a regression problem, it is recommended, and then you should get this weight and the cylinders, all the variables, try to get into a same scale. Okay, so you can get this into a scale, same scale. One way is to get into a scale between 0 and 1. There are different ways of scaling. You can divide it by the maximum value of each column, right? Then you will obviously get a value between 0 and 1. Or you can get something called min max scaling. So you can, that's also getting into a same scale. You can get the z score out of it. Like, so you can, that we call a standardization. You can do scaling, standardization. By doing those, you will avoid that difference between the ranges of the variables, right? So you can practice that. So we will learn about scaling and standardization in the coming lesson. Okay, so that's one thing you can do. If you wish, you can practice a simple scaling, yeah, divide by the maximum value. Or if you wanted to find out what is min max scaling, you can apply that and retry the training this model again and see whether you see any difference. Okay, the third one is how we can determine the set of features to be used for training. So you can try to get few things from the correlation metrics. We will learn about this again when we are doing the model, different model algorithms in the future lesson. You can find out whether any variable is having a good correlation with the target variable. You can think like that is a good predictor variable. So you can use that as the priority. For example, if you go here for the correlation metrics, so let me see. You can see that's why that's one reason I use weight and miles per gallon. It is having the highest correlation when it's negative, weight and miles per gallon. And you could also use the variable horsepower alone. This is also higher correlation. Displacement and the miles per gallon, higher negative correlation, but it's strong. And so this is the weakest correlation. If you wish to drop any variable, you can try dropping acceleration or model year. Like that, you can think of like, what should I give the higher priority? There are other ways we can decide whether which variable should be in the model, which variable should not be. And if since in a linear regression model, we have to follow something like the collinearity. So if two variables can make another variable, if you can replace two variables by one variable, or two variables are core, so make a collinear relationship, so that makes the variable you can disqualify, or you can remove the other variable in the model, because it will not give you the model training. But you will get your model training process will complain you, because you cannot settle in one solution. I will come back to this when we are discussing linear regression models under supervised machine learning algorithms. Okay, so therefore you have many ways and techniques you can decide which variables to be used, which variables should not be. And should you train one model only? I think you have the answer for this one now. Should you? No, you cannot get away with one model. That's for like a study project. If you get done with a tutorial, it's fine. You can train one model and get done with it. But actual work, you need to train more than one model. Sometimes we train 100 models, sometimes like 10, 20 models. You have to do a lot of trials. You have to try out, like I mentioned, try out different algorithms, different combination of features. Within same algorithm, you can try different hyperparameters to change behavior of the algorithm as well. So there are like a lot of things, lot of work involved. It's not just simply writing a function and training a model and say I'm done. It's not that. Okay, so you have to train a lot of models and compare them. So that's why the model evaluation lesson we will be doing in future. So will be very important how we can evaluate the models and compare them to find out what is the best model I should be using in the application. Right? Out of the, if you build 100 models, you have to choose one. Sometimes we will be using another technique. You can use not only one model, we can use maybe 2 3 best models together. We can call it them ensemble model, or we can call it there's another way, stacking. We combine multiple models, output from another model is going to another new model, and like that. So ensemble model, we are using multiple models, prediction from all we are taking together and making another model, or building another model to make the final prediction. So there are ways you can do that. Right? So in terms of that topic, so in that along that topic, I have wanted to get you introduced to another method called automated machine learning. So which we are not going to cover in this class or this course, but there's a technique available in almost all the cloud platforms, Microsoft Azure, uh, in IBM Watson, or Google Cloud platforms, or AWS. So when you are using the machine learning platforms for your model building, you can find automated machine learning, or auto ML. So which makes uh, you send the data in, you upload your data, but you should still have to have understanding what are the features you should be using. You have to do some selections. You have to, for that auto ML algorithms, you have to provide all the details about your features and what you do, what you wanted to do. Right, the automated ML are not intelligent, not run on AI. It will run as an algorithm per your instructions. Give proper instructions. You have to learn this concept. That's why this learning is very important. Keep that in mind. Automated machine learning will not help you if you don't know how to use the machine learning concept. Okay, you have to select features. Like at least you have to give the all the features or potential features. It will decide what are the best features to be used, but you have to give all the potential features. Those are like things you need to mark in a graphical user interface. And then you have to provide what type of algorithm you need to use, you should not use. So the algorithm will decide. Okay, it will not try out all the algorithms unless you say otherwise. You will be consuming a lot of computational resources, because for regression there could be 10 plus algorithms available in the cloud platform or auto ML tool. But from your understanding, you should have some idea which algorithm should you try, which algorithm should not try. You can instruct the AutoML tool, okay, try these algorithms only, okay, and then that will be used. And then for the evaluation, there are many ways of evaluating. You need to decide. uh, we will discuss in detail for different machine learning problems. Your evaluation metric should be chosen based on the application. Sometimes we have to use one metric, but not for the other application. You have to use a different metric for that application because the requirement change, and we need to track a specific requirement to select what is the best model, right? If you wanted to test someone for to be a doctor, you are going to test with some medical questions. So if you are going to test someone for engineering profession, you want to test with a different, like, not subjects we can think of, like good in math, good in biology, that kind of, at least that one. So you can think each application your machine learning model should be evaluated properly. So for AutoML tool, the AutoML will only help you to build get the best machine learning model by training hundreds of models automatically within the system. You will not interfere with the training process, but initially you need to provide some limitations. What are the algorithms you should be choosing, not to be choosing, and then what are the evaluation metrics you should be using to get the best model, right? Such as, and what are the features you need to use or not to use. Those decisions you need to make, and you need to provide to AutoML tool. Then AutoML tool will build hundreds, maybe a few hundreds of models internally, and give you the best model out of it. So that's why it's just a side note that will help you in the future, because in future we will be doing that. When we have time, we will also discuss some thing about the AutoML, but that will not be a major part of this course. Okay, so the last one, what can you say about the prediction from the model we trained above? So I already mentioned to you the model we train is kind of over predicting. It's predicting the value than higher than the actual value almost all the time, except like few examples. Okay, so we will come back to all of these in our future lessons, and we will discuss in detail. Just gave you some general introduction how we can use scikit-learn library, and then I hope you get some idea of what is ahead in terms of model training, and what are the things you should be familiar with from the scikit-learn library. This framework will be continued, and these steps will be continued in our future lessons as well. But only thing will be, I'm adding new content in between, and I'm improving your understanding in each of these topics, right? Okay, so this is end of the this notebook, and I hope you learned something good today, and see you all in the next lesson.